dear students. Myself Shraddha Punda, lecturer in Electrical Engineering Department, Kekewak Polytechnic, Nasik. I welcome you back in my educational video channel. Today in this video, we will discuss very important phenomenon in electrical engineering, that is electromagnetic induction. So let us start with it. What is an electromagnetic induction? The phenomenon of electromagnetic induction simply says about how the EMF gets induced in the coil or conductor, or simply it tells about how the EMF or voltage is generated or produced in the coil or a conductor. So electromagnetic induction means the generation or production of voltage in a conductor which is placed in a magnetic field. So in this diagram, you will see the construction for the AC generator, where you will observe the two poles of permanent magnet which creates the magnetic field. And there is a one coil which is rotating in that magnetic field. The two slip rings are attached to it and the two carbon brushes are there in order to collect the current. So once the EMF get induced in the coil or a conductor, current will start flowing. So this is how the EMF gets induced according to the phenomenon electromagnetic induction. The output of AC generator will be like this. So you can see here the EMF or the current is zero. Once the coil starts rotating in magnetic field, it will try to cut the magnetic flux, and that will result into EMF induction in the coil or a conductor. So as soon as there is a cutting of flux by the coil or a conductor, EMF get induced, and when the magnetic flux gets cut by conductor are maximum, at that point EMF will be maximum. So you can see in the waveform, according to the position of rectangular coil in a magnetic field, you will get output. Now we are going to see the Faraday's law of electromagnetic induction. Michael Faraday was the English scientist who contributed to study of electromagnetism and electrochemistry. He has introduced two laws of electromagnetic induction. They are known as Faraday's first law and Faraday's second law of electromagnetic induction. Let us see first what is Faraday's first law. Whenever the magnetic lines of force linking with the coil or conductor changes, an electromotive force gets induced in that coil or a conductor. So in the first law of Faraday's law of electromagnetic induction, it is stated that how the EMF gets induced in the coil or a conductor. And there is a presence of EMF in the coil or conductor because of change in magnetic lines of force linking with the coil. Such a EMF is present as long as this change is taking place. So you can see in the diagram, whenever there is a change in magnetic field associated with the coil, EMF get induced, and that can be seen by the galvanometer deflection. Let us move for the second law, that is Faraday's second law of electromagnetic induction. In this law, it is given that what is the magnitude of EMF induced. The Faraday's second law statement is the magnitude of induced EMF is directly proportional to the rate of change of flux linkage. So that flux linkage is nothing but number of fluxes into number of turns of the coil. The expression for induced EMF is given by E is equal to N d phi by dt, where N equal to number of turns in a coil, d phi by dt is the rate at which the magnetic flux gets changed. Now we will see how to find the direction of induced EMF. This can be found out by using the two laws, Lenz's law and the Fleming's right-hand rule. So what is there in Lenz's law? The direction of induced EMF, which is produced due to electromagnetic induction, is always such that it will oppose the cause behind its production. So we can write EMF induced in the coil or a conductor is equal to minus N d phi by dt. Here the negative sign indicates that the direction of induced EMF tried to oppose the cause by which it is produced. The next is Fleming's right hand rule. For this rule, we have to consider our right hand and the three fingers. If the three fingers of the right hand are kept perpendicular to each other, then the first finger, that is forefinger or index finger, indicates the direction of flux lines, that is from north to south pole, and the thumb indicates that the direction of conductor motion, and the second finger, that is middle finger, is in the direction of induced EMF or current. Now let us see what is the nature of induced EMF. The change in flux linkage with the coil or a conductor can be obtained by the two methods. The two methods are dynamically induced EMF and second is statically induced EMF. In the dynamically induced EMF, conductor or flux lines are rotating. In statically induced EMF, the conductor or flux lines are constant. So the nature of induced EMF is of two types, statically induced EMF and dynamically induced EMF. Statically induced EMF is further categorized into two, self-induced EMF and mutually induced EMF. Let us discuss in detail. In the dynamically induced EMF, you will see there is a presence of EMF induction in the coil or a conductor because of the physical movement of the coil or a magnet. Let us see the two cases. In the first case, you will observe the direction of conductor is exactly perpendicular to the magnetic field. In the second case, it is not exactly perpendicular, but it is making some angle, that is theta. So theta is the angle made by the conductor with respect to magnetic field. So EMF induced in the first case is BLV, where B is magnetic flux density, L is the length of conductor and V is the velocity of conductor. And for the second case, the EMF induced will be BLV sin theta. Now let us discuss statically induced EMF. It is further categorized into two types, self-induced EMF and mutually induced EMF. So let us see what is self-induced EMF. The self-induced EMF is the EMF which is produced in the same coil due to the change of its own flux linked with it. If the current of the coil is changed, then the flux linked with its own turns will also change, which will produce an EMF that is called as a self-induced EMF. In the diagram you will observe there is a one coil to which one battery source is connected and one resistor is there. The resistor is variable. Once the resistance value gets changed, the current flowing through coil also change. That will change the magnetic flux associated with the coil and the result is EMF induction in the same coil itself. That is why we are calling it as self-induced EMF. The next we have mutually induced EMF. Mutually induced EMF occurs in between the two coils. Let A and B are the two coils which are placed very close to each other. If coil A is joined to a battery, one switch and one variable resistor and coil B is connected to galvanometer, let us see what will happen. When the switch S is closed in the first diagram, the current will start flowing through the coil and that will produce a magnetic field which is shown in the diagram by red colored dotted lines. They are partly linked with the coil B as well. As the current through the coil A is changed, the flux linked with the coil B also changed and according to Faraday law of electromagnetic induction, the EMF is produced in the coil B as well and this is what known as mutually induced EMF. Now let us see the expression for the self-inductance of a coil. So here we have considered one coil and I is the current flowing through that coil. The capital N represents the number of turns in the coil. So according to Faraday law of electromagnetic induction, we have seen E equal to minus N d phi by dt. But we know that magnetic flux is equal to magnetic flux density into the area. So that can be written as mu into H into area. But we have gone through that magnetic field strength H is equal to N into I upon L. So we can put for H. So expression will become mu is equal mu Ni upon L into A. So this can be put in the expression E equal to minus N d phi by dt. So the expression becomes E equal to minus N d by dt of mu N A upon L into I. So that can be further written as minus mu N square A by L di by dt. But this is what the self-inductance is. So E is equal to minus L di by dt. So this is called as the coefficient of self-induction or simply the self-inductance. You may call it as inductance only. So we are getting for L mu N square A upon L, and unit for the self-inductance is Henry. Let us see the mutual inductance of a coil. We have just gone through the phenomenon of mutual induction. Again here we are going to consider the two coils which are having N1 and N2 number of turns, and those coils are placed near each other as shown in the figure. So E2 is equal to N2 d phi 2 by dt. N2 is equal N2 dk phi 1 upon dt. So that can be further written as N2 k1 d phi 1 by dt. This is what we are writing because there is a EMF induction in the second coil because of change in current in the first coil. So phi 1 can be written as mmf upon reluctance. So that is equal to N1 I1 upon L1 by mu A1. So finally you are getting N1 mu A1 upon L1 into I1. So for E2 we further write N2 K1 d of dt N1 mu A1 I1 upon length L1. So that is equal to K1 N1 N2 mu A1 upon L1 di1 by dt. So we are getting finally the EMF induced in the second coil, that is E2, equal to M di by dt. This M is called as mutual inductance, or you may call it as coefficient of mutual induction, where M is equal to K1 N1 N2 mu A1 upon L1. Similarly, if we calculate the induced EMF in coil 1 due to the change in current in the coil 2, we can find the induced EMF E1 in coil 1. So that can be written as E1 equal to K2 N1 N2 mu A2 upon L2 di2 by dt. So M is equal to K2 N1 N2 mu A2 upon L2. Now multiplying the expression for M in above, you will get M square is equal to K1 K2 N1 N2 N1 N2 mu A1 mu A2 upon L1 L2. So M square is equal to K1 mu N1 square A1 upon L1 mu N2 square A2 upon L2. So that can be written as M square is equal to K1 K2 L1 L2. So mutual inductance is equal to under root of K1 K2 under root of L1 L2. So which is equal to K under root L1 L2, where the K is called as the coefficient of coupling. Let us see what are the applications of electromagnetic induction. In electrical engineering, you will observe many of the machine works on this phenomenon called electromagnetic induction, such as AC generator, electrical transformer, some magnetic flow meters, and electronic instruments. Let us summarize what we have discussed in this video. We started with the phenomenon electromagnetic induction. we had discussed Faraday's law of electromagnetic induction, in which we have seen the Faraday's first law and the Faraday's second law. Later, we have seen how to find the direction of induced EMF by using the two laws, Lenz's law and Fleming's right-hand rule. We have seen the nature of induced EMF, dynamically induced EMF and statically induced EMF. Also, we have seen self-induced EMF, mutually induced EMF, self-inductance of a coil, mutual inductance of coil, and lastly we have seen what are the applications of electromagnetic induction. Thank you for watching my video.